Let's get a little deeper into the water in the atmosphere itself. Obviously, we can define an integrated water in the air column, atmospheric column, which depends on integrating the water vapor from the surface to the upper atmosphere. Z is some height. Obviously, as we remember, the water vapor quickly dries off as you go into the upper atmosphere, and also as you go to higher latitudes, because the temperatures get colder, and even in the deep tropics, the water vapor that's pumped into the atmosphere through evaporation and convergence and advection and so on is going to convert to rain at some height and then get dry by the time it hits the tropopause, except few locations where the stratosphere is getting a little bit of water across the troposphere. We will see that cold trap a little bit later on. Looking at the integrated curve in terms of total water or liquid water and ice form in millimeters, so you can integrate it and convert it into a millimeter of water equivalent. And there is the sea surface temperature. We have seen, this is the liquid and water ice in a dashed line here, shown as a scale on this side. Obviously not as cleanly distributed as the water vapor. Water vapor is what we remember from before. You go to high latitudes, you get drier, and water vapor drops off in terms of millimeters. And of course, there is still this asymmetry, hemispheric asymmetry, because of the land and ocean distribution. So you can see this drops to a lower value than this one. And the liquid and water ice have this ITCZ and the storm track relation that we talked about before, that we will come back to later on. But the main point is almost all of it is as water vapor, with the tiny bit present in liquid form and ice because of how cold the upper atmosphere is and how long the grapple and ice stay in the air. And there are times when you have these massive atmospheric rivers that are carrying elevated levels of water as well, depending on the various parameters. Looking at the relation between sea surface temperature and, again, our favorite Clausius-Clapeyron, and the seasonality of the water vapor, now in kilogram per meter squared, so this is not integrated. And you see the nonlinear relation we expect as we get into these temperature ranges. The curve becomes much more parallel to the Clausius-Clapeyron, as we remember from before, and the seasonal difference of the total here disappears, whereas the seasonal difference is more contrasted at lower temperatures. So just remember that. And if you look at the change in temperature or the difference in the change in temperature as a function of latitude for season, so this is basically between moist and dry ascent. If you raise a parcel that's dry, we call it adiabatic, basically because it's moving so fast that it doesn't mix with the environment. Okay, that's a concept you should remember. It's a very strong concept in meteorology. We don't talk so much about it in climatology and oceanography and so on, climate science, but it's the air parcel that's moving, which is dry, means it expands and cools adiabatically, whereas if the air parcel has water vapor in it, then as it rises adiabatically also, the water vapor within can condense and release heat and change the rate of temperature drop with the rise. Remember, pressure drops off, right? So obviously there is a seasonality to it, because the water vapor content in the parcel itself is going to be different based on seasonality. So what is shown here is the difference of the temperature you would get if the air parcel was dry versus wet. Okay, so moist versus dry ascent. Its positive means that a moist air parcel is going to be warmer by several degrees, and it's got more moisture, so will be the temperature difference will be more in June, July, August. Is it clear? A moist air that's rising from the surface into the atmosphere is going to expand and cool. So even if it doesn't exchange heat with the environment, that expansion is going to cool it, but the cooling will be much slower if there is water vapor in it, which is going to condense and release heat. It's a very simple concept. We can add lapse rate and hydrostatic balance at this point. Basically, lapse rate is the rate at which the temperature changes with height. So that's obviously dt dc, temperature rise with temperature change with height. It just comes down to minus g over cp, which is not derived here, but you can do it very easily by taking the ideal gas law, and Cp is the heat capacity of air, which we call the dry adiabatic lapse rate. We will see that it quickly gets complicated when we add water vapor to it. So you know the hydrostatic balance equation. I'm going to add a podcast on how we actually derive it. This book is not written exactly as a very basic text which describes, which derives all these things, equations of motion, etc. Just jumps into it, but we will do that just to give you an example. So dp dz is minus rho g as delta z goes to 0, because you take P1 minus P2 divided by delta Z, it gives you minus G rho, where you are assuming that the environment is in such a balance that the pressure difference is only going to be related to the mass above it. There are no motions to disturb the hydrostatic balance. Why is it important to look at these together? Because when you talk about displacing an air parcel, it's critical not only to remember that we are making this adiabatic parcel assumption, but also that it adjusts quickly to the pressure of the environment to maintain hydrostatic balance. Basically, the pressure at any point is going to be the weight of the air above it. So when you look at per unit volume, it's going to become density times gravity. If you multiply by volume, you get weight, right? So P1 minus P2 divided by delta Z. So if you take a air column going from height Z1 to Z2, the delta Z, the pressure change is going to be determined by the weight of the air that's there. Because you are driving the delta Z to 0, you're going to assume the density to be the constant reference density at that level, which is obviously not true. In the atmosphere, the density changes quite a bit. So when you look at water vapor that's included in it, without going into the details of the derivation, the saturated lapse rate in the atmosphere is related to the dry lapse rate through how much water vapor there is and the ideal gas constants. So saturated air versus dry air. You are still talking about water vapor, so it is still behaving like an ideal gas. It's not water, it's just saturated with water vapor. Okay, so remember that. And this R here is the ratio of those two. Okay. So this is again a complicated looking relation, but just remember again the nonlinear dependence of water vapor on temperature, and there is this temperature squared term in it. This is where this difference comes from. Why dry adiabatic lapse rate and moist adiabatic lapse rates can be so different. So here is the moist adiabatic profiles defined by this equation, looking at various temperatures and the rates of the drop. What do you expect? You go from high pressure at the surface to low pressure towards the top of the atmosphere, and when you have colder temperatures, the moisture is going to be very low, so the lapse rate is going to be closer to the dry adiabatic lapse rate because the air is almost dry. But as you get into warmer temperatures, you can see that the drop in Kelvin per kilometer is going to drop off quite rapidly. because of this process of condensation and heat release in the moist adiabatic rise. Okay, very simple concepts, but you have to remember them. I like looking at the figures because the equations look very complicated and nobody is going to remember them by heart unless you did it for 30 years or so. But these tell you quickly how much you have grasped the concept itself. Colder air, drier air, moist adiabatic lapse rate is going to get closer to the dry adiabatic lapse rate, which is about minus 9.8 Kelvin per kilometer. Okay. There are other details we will see later on, that the atmosphere is stable to dry convection but not to moist convection, and so on and so forth. So we'll add other details, but we will leave this here. In the next podcast I'm going to add the derivation of the hydrostatic balance, which is fairly straightforward, but if you haven't done derivations of equations before, it's a good simple example to look at.